Okay, so our last unit is on bonding, and I've mentioned this earlier already today. Chemical bonding is a very different kind of chemistry unit. It's very theoretical, and one of the reasons why is that bonds don't really exist. They do and they don't. Okay. When you guys think of molecules, you probably think of pictures that look like this, where like here's an atom, and in between them is a bond. But that's not what actually is occurring. There's not actually like a stick between two balls. Okay, it's a good way to conceptualize what we think is happening as like an artistic in a 3D realm, but that's not true. A bond is actually an attraction between two different things sticking together. In my mind, I think of magnets. You know how like you have magnet 1, magnet 2, you put them together and they stick together? Is there actually something in between there that's like gluing them together? Well, no, there's not actually a glue in between there. And it's the same thing with bonds, but we draw lines in between to try to represent what we think is happening. Typically, these lines right here are sometimes indicative of electrons. And here becomes one of our first problems with this unit. I said this earlier. Electrons are pretty much the smallest subatomic particle we know of. Okay, if you think of like the periodic table being fairly small stuff, they're made up of protons, neutrons, and electrons. Electrons are as small as they get. And electrons are basically the key to how we think bonds form. Well, when you want to talk about looking at stuff that's really small, we use microscopes. The microscopes I have in our classroom are light microscopes, and they don't have a hope in the world of being able to pick up an electron. The best microscopes in the world, the ones that run like $10 million, are actually electron microscopes. Have you guys ever heard of these before or talked about them in class? Okay. Basically, what an electron microscope does is it shoots electrons at a specimen. And based on whether the electrons bounce back or go through, it makes a picture of the specimen. Okay, here becomes a problem. If you imagine that you're shooting electrons at something to try to figure out what it's made out of, and the bond consists of electrons, how well is that going to work? Not at all, basically. So the first thing I need to tell you guys about this unit, I actually have written on one of the slides here. Using advanced microscopes, we can just barely detect atoms. We have no visual evidence for bonds. So like when we draw pictures of this stuff, this is just a artist's rendering of what we think is happening. You guys have seen the Magic School Bus before at some point, right? If Miss Frizzle and her Magic School Bus kids could like zoom the bus down to the smallest size possible, honestly, we have no idea what it would look like. It's too small. And that's one of the weird things about this unit. So all of our bonding is really, it's based on either logic or very indirect evidence. This is one of the units where I really like kind of sharing some stories about science and how it evolves. In the physics world, for example, scientists used to believe that the Earth was flat. And scientists used to believe that the Earth was the center of the universe and the sun runs around us. And I think this might be one of those times where 500 years from now, in some sort of Jetsons space age kind of thing, I don't know what they're going to teach, but I feel like there's a good chance that might not be this. Does that make sense? Where like our ability, our tools, our understanding of this is so limited right now that it's piecework, it's guesswork, it's logic. We think we're right, but the number of times that scientists in history thought they were right and were not, I don't think that we can even list them all. Does that make sense? Even in chemistry, we talk about different models of the atom. You guys remember learning about, like, say, the Rutherford model of the atom or the Dalton model of the atom? I don't think we talked about that, but maybe you've heard that before. Well, like, physicists are working on the quantum model of the atom, which really fits with this. Long story short, I'm rambling. We think we know what we're talking about, but I always want to preface this by saying that 50 years from now, we might teach something different, which I think is really cool, by the way, because I don't think there's really anything else that's quite like that in school, where when a teacher has to start by telling you, and by the way, this could be wrong. How crazy is that? But this is what we know up till now. So, there's a cartoon there in case you've ever seen Pearls Before Swine. Okay, our journey today starts in 1904, which, if I've talked with you guys much before about dates for chemistry, that's like hardly at all ago. Boy, that's the worst way of saying that. That's a very short period of time ago, 1904. Like, we're basically talking 100 years, which in terms of science is like a blink of the eye. right? Like the amount of technology leaps that can happen within 100 years is, right? Who knows where we'll be in another 100 years? That makes sense? So back in 1904, Abegg basically has this idea that bonding must be somehow associated with electrons. Now, I think you guys, without me even having taught you this course, you might have already known that electrons somehow have to do with how bonds form. Actually, I guarantee you should have known that because we've already talked about cations and anions. Pardon me. Where, like, say, sodium has to lose an electron and chlorine has to gain an electron. Like, we've talked about this at some point before. And the crazy thing is if you went to school 100 years ago, they didn't know this. The things that we just take for granted now about cations and anions. And he came up with this idea called the octet rule, which I think you guys have probably heard at some point before, where everything wants 8 electrons. You guys know this term, valence electron? We've used that before. So like here's lithium. Lithium has 2 electrons at a lower energy level. And then its third electron is a valence electron. So that's why lithium often is a plus charge, because lithium would just love to get rid of that electron. And if it loses the electron, it becomes positive. Is that something you guys remember? Whereas helium has 2 valence electrons. It's actually considered to be full. And helium then is a noble gas because it doesn't react with anybody. Basically, the idea then that scientists have now come up with, and again, this may change 50 years from now, but we think that electrons inhabit regions of space called orbitals. It's actually like one of the first definitions I need you guys to know, the term orbital. The definition is basically it's a volume of 3-dimensional space where we think electrons might be. There's a lot of overlap with physics here. So I know I'm not in physics yet, but I'm sure I'll teach a bunch of you physics next year. So I'm just going to tell you anyways. There are some really weird theories about how electrons work. The basic long and short of it is that electrons are so small that as soon as you start looking for electrons, they've already moved. Okay? Let me see if I can give you an analogy here. How do I perceive that Walker is sitting there? Like, how do I know that he's there? Well, from a physics point of view, light has bounced off of Walker and then come to my eyes, and my eyes then recognize that Walker is there because of the light that bounces off of him. Does that make sense? Well, using that same logic, how can you tell if an electron is there? Well, what you would do is you would bounce some light off of an electron. The light would bounce off of the electron to your eyes. Now, granted, your eyes can't see, but imagine you had a detector that could see an electron. Light would bounce off the electron, bounce to the detector, and then you know the electron is there. Here's the problem. The electron is so small that light itself will cause the electron to move. And so as soon as the light hits the electron bounces somewhere else. And then when the light then bounces to your eyes, you think that the electron's right here, but it's over there. Does that happen with Walker? Does light bounce off of Walker and cause Walker to go violently crashing across the room? Well, no, Walker is a big enough person. I don't mean to say you're big, but Walker has enough mass to him compared to an electron that light will actually bounce off of him and he'll just stay in place, right? But electrons are so small that we cannot even perceive them because as soon as we attempt to, they're already gone. Does that make sense? So it's a very physics kind of concept. Long story short, we do not believe anymore that electrons go in these like orbits. Because as soon as we look for the electron, it's already moved. And so we try to draw electrons in what are called orbitals, which are kind of like balloons. And we think that somewhere in the balloon is the electron. The only problem is we just have no idea where. Like, we know it's somewhere close because we were able to perceive where it used to just be, but we don't know where it is anymore now because its location has changed. It's called the Heisenberg uncertainty principle. Maybe you guys have heard that from Heisenberg from Breaking Bad. That's actually what he named himself after, Heisenberg. This uncertainty principle basically says, I don't know whether the electron is there or there or there or there or there or there. As soon as I look for it, it's going to be gone anyways, but I know that it's about in this area. Does that make sense? And so we draw these different bubble shapes as to where we think electrons are. Here's the first thing I need you guys to be able to memorize, I guess. We believe that orbitals can either have no electrons, 1 electrons, or 2 electrons. We've actually already talked a little bit in this course about how orbitals don't have to have electrons. You guys remember when we did the flame tests? The reason why flame tests burn different colors, like why fireworks burn those bright colors, is because what ends up happening is when you excite and heat up an electron, you give it energy, and it jumps from this orbital to this orbital. And it can go from an orbital that it currently was in to an orbital that has no electrons. And then if it finds an empty orbital that it goes to that has no electrons, when it comes back down to its original orbital, then it re-releases energy in the form of light. So we're talking about that at all? So you can actually have empty orbitals, that's fine. In my mind, I think of like a hotel, where you've got all these different rooms in the hotel. Some of them are filled, and some are empty. And if you wanted to, you could take your room 105 and just go over to room 212 for a little while. Kind of like when Melissa and I were on our honeymoon, we asked them, hey, we're on our honeymoon, and they bump us up to the honeymoon suite for a night kind of thing. That's kind of like the electrons getting to go to a different room and back, because it's empty. I don't know. Yeah, that should make sense. Valence orbitals, then, are the ones that are considered to be at the highest energy level possible. So, long story short, we don't think electrons actually orbit. We actually have no way of knowing where they are. They move as soon as we look for them. There are so many weird properties that we'll get to in physics otherwise. But basically, it's a space where we think they exist, probably. Now, honestly, that is really confusing for most kids in grade 11, even, to be honest. So when we taught you guys, well, I didn't teach you, but when Lab taught you, yeah, probably just Lab, taught you about chemistry for the first time, you probably drew these things called dot diagrams. You guys ever do these before? Where you draw like dots based on electrons? So basically the idea is that maybe this is a simpler way of drawing it, because trying to draw three-dimensional bubble orbital type things is confusing for like a grade 9 kid. So we just draw them like this instead. And so this will work a lot of times. We actually call these things Lewis symbols, if you haven't heard that term before. And so it's pretty straightforward. You guys have done this before. Here is basically a picture I found on the periodic table that just shows you all the Lewis symbols. And I think it's intuitive because you can see how the electrons work. Hydrogen, and everybody in group 1, just has one extra electron. Whereas everybody in group 17 over here, I don't know why they didn't write that with 17. All of these guys right here are all missing an electron. That's how like their bonds form. You have an extra, you need one, perfect. Does that make sense? Whereas everybody in the last group over here, they have they're full, right? So therefore they don't even make bonds whatsoever. Technically, again, I kind of blur this into my physics lesson a little bit just because it's a good enough time to. I'm not always going to test you on the physics stuff. You know how I said you can have up to 2 electrons in an orbital? We've discovered some really cool properties, physicists that are working nowadays, about how electrons work. They believe that electrons are considered to be entangled with each other. They have some really cool theories about how we might be able to do teleportation using electrons. Long and short of it is that whenever you have 2 electrons inside an orbital, one of them spins this way, and the other one spins the other way. I have no idea why. We're still trying to figure that out yet. But one of them always spins clockwise, and one spins counterclockwise. So you might actually see some pictures like this in textbooks, where you have an up arrow and a down arrow. And those up and down arrows refer to the direction the electrons are spinning. Just so, in case you ever see that somewhere. So right here, you have a full orbital of 2 entangled electrons. And then this electron right here, this guy's the key electron. He's not full. See, orbitals that are empty, they're kind of useless. Orbitals that are full are also kind of useless. But it's these half-full orbitals that only have 1 electron. They're what we believe make bonds. Because if you have an electron and you have an electron, well, now we can merge them together. Does that make sense? So it usually involves, yeah, I guess that'll work here. The Pauli exclusion principle basically says that you can never have more than 2 electrons. It's actually a very odd concept because what's the charge of electrons? Well, negative. What do negative things do next to each other? If this is negative and this is negative, shouldn't they? They don't. That's like the what the heck is going on thing. See, what ends up happening is these 2 electrons right here in a full orbital, and these 2 electrons right here in a full orbital, they repel each other. A group of 2 and a group of 2, they repel each other. But inside an orbital, for some reason, 2 electrons inside the same orbital, they don't try to break away from each other. I would say, does that make sense? But it actually completely doesn't make sense. This is kind of the weirdness of trying to learn about this last unit here, is that we're still trying to figure it out. Okay. Here's some more pictures of orbitals. if you get to this point in chemistry, at some point you'll hear about things called s, p, d, and f orbitals. Basically, the way it works, you can actually see it here on the periodic table. Everything that goes in pairs right here, these first two things, are all known as s orbitals. These guys right here are known as p orbitals. And see how there's 2, 4, 6? That actually means that p orbitals often will have like more than one dimension to them. See how like the s orbital is just like a sphere to it? Whereas like the next p orbital, see how there's like different regions to it? That kind of is based on there needed to be like a group of 2, another group of 2, and another group of 2. So then the d orbitals are everything inside here. And then the, d blocker right here. And then which one am I missing? Oh, F. F should be these guys down here. You guys remember maybe a while back I told you that when we count valence electrons, we kind of count like 1, 2, skip all these guys right here, 3, 4, 5, 6, 7, 8. We'll be talking about how you skip the transition metals. This is kind of one of the reasons why, is that the orbital regions of space that these electrons take up, everything that's a transition metal, they get kind of like their own unique orbitals. So it's almost like if you like the hotel analogy, this guy, this one, this one, this one, this one, this one, this one, they're all part of the same hotel chain. Whereas all of the electrons that fit right here, they're in a different hotel. So that's why we have to count them differently. It's just kind of the way that the electrons fit together. Does that make sense? Okay, let's try a task here. Draw me the Lewis symbols for helium then. So to draw a Lewis symbol, first thing you need to do is just write out the element symbol. So He. And then we just need to know how many electrons helium has. How many electrons does helium have? Okay, first question. How do we know how many electrons something has? What number is it? It has 2 electrons. Okay. How many electrons can be in an orbital? Up to 2. Okay. So the way we draw them then is the top, left, right, and bottom, basically each kind of representing an orbital. So rather than drawing it like this, that would be wrong. Because what this kind of implies is that you have an electron in one orbital and an electron in a different orbital. But the way helium will work is helium will have 2 electrons in the same orbital. Kind of like what we're trying to do is represent like this top side right here is like a bubble. And there's 2 electrons in that bubble. Now, I don't care whether it goes on the top, bottom, middle, or wherever, but make sure you put the 2 dots side by side. Let's try calcium. How many electrons does calcium have? 20. Has 20. But are we going to draw all 20 of them? Because some of them are in filled valence orbitals. Does that make sense? And we don't want to draw those ones. We only want the outermost energy level ones. So looking at calcium's position on the table, how many outside electrons should it have? 2. Okay. Now what happens here is we're actually going to split these ones up, though. Now this may seem crazy, because you might say, Chris, didn't we just put the helium ones together? Why are we taking the calcium ones apart? Anyone have a good rationale as to why? What do we know about helium and its location on the periodic table? It's a stable, noble gas. Does that make sense? Should helium be able to form bonds? And the answer is no, it's in the noble gas column. Does that make sense? However, calcium's a little bit different. Calcium has a +2 charge normally. And here's the reason why. Here is an electron in an energy level. And here is an electron in another energy level. And it has 2 individual electrons, both able to go out and make some bonds. If both of these electrons were in the same orbital, would calcium be able to make bonds at all? No. And that would be a huge problem because calcium is a huge part of a lot of the things we have in the natural universe, like chalk and teeth and all that stuff, right? If calcium were unable to bond, that would be a huge problem. Okay. Are there any other orbitals in calcium? Yeah. I mean, technically, we could even draw like an orbital down here and an orbital down here, but is there anything actually in there? No, that's fine. We don't have to have those orbitals filled. That's not a big deal. By the way, we don't usually draw these little bubbles. I'm just drawing them for you. So try strontium. What would strontium look like? How many electrons does it have total? Okay, now we're not drawing 38, obviously. That's a little crazy. So how many do we actually need to draw? 2, yeah. 2. And again, should we pair them or separate them? Yeah, a logic would probably dictate that we need to have one here and one. I don't actually care where. I'll put it on that side. Just make sure they're not next to each other. Because if you put them next to each other, it implies that it's a full orbital and it can't form any more bonds. So we need them separated. What about chlorine? How many electrons does chlorine need to have total? Okay, now in terms of its electrons that we care about, then we got to start counting from the far side over. So sodium, magnesium, all the way over. Chlorine needs 7. Does that make sense? So the way this might look is that first you'd start here, and then here, and then here, and then here. You'd spread them all out. But then at some point, these electrons, they got to start bunking up into groups of 2. So I don't care where the extra group is, but there needs to be like a full one, a full one, and a full one, and then there's one that's left over. And this guy right here, that's the key electron. It's what allows chlorine to make a bond, because it's kind of an unpaired up electron. What about sodium? What's sodium look like? You got the hang of this by now. It's got 11 electrons. How many does it need? Just 1 dot. I don't care where. You guys have already learned this concept then. Why does sodium and chlorine fit so well with each other? Why do we have salt? Well, this guy has an electron. That guy has an electron. They just fit together. Does that make sense? As crazy as this seems, people only started figuring this out about 100 years ago. That's what I love about chemistry. It's like we are still learning about this. 100 years ago, we were starting to figure this out for the first time. Okay, here's some definitions I need for you guys to have. Because like I said, this unit is a huge definition unit. So we've already talked about the octet rule. Everything usually wants to have 8 electrons. A lone pair would be this. I think the word lone pair was probably poorly chosen. I find a lot of kids, they think that things that are alone are the singles. And so they might think that this guy right here, that's a loner, he's alone. But the problem is that the reason why it's a lone pair is that it's a pair that gets left alone. Can these electrons bond? No, they're full. Does that make sense? Their orbital group of 2 is full. So this thing right here cannot form a bond. Here is another lone pair. This guy right here is also a lone pair. The other definition, if you're not a lone pair, you're a bonding electron. See how there right here is a single electron right here? Bonding electrons are the singles. And from what we seem to understand, it's the single electrons that are really the key to how matter sticks together. So lone pair is a group of 2. Bonding electron is a group of 1. Can you have a group of 0? Technically, yeah. Well, it is possible. Like when we drew sodium. Sodium back here has a group of 0, or a group of 0, and a group of 0. That's fine too. It doesn't have to have orbitals filled up. So, like I said, about 100 years ago, scientists are starting to really piece this together and try to figure out at least what we think now. And they're trying to ask the question, well, why do electrons want to go with each other? Because isn't that kind of a fundamental paradox? You guys know what a paradox is? You know what that is? Like something that just seems, I don't know, opposite to what you'd expect, I guess. That's the definition of it. But why do 2 electrons stay next to each other? Shouldn't 2 electrons want to repel each other? Does that make sense? No, in fact, it doesn't make sense. Why do 2 electrons fit in an orbital? And so Linus Pauling came up with this idea of electronegativity. And I'm big on analogies. I like to think of this as like a King of the Ring cage match kind of thing, or maybe like a UFC ring kind of fight, where everyone's kind of like a ranked fighter, and certain compounds, just for whatever reason, we're still trying to figure out maybe the whys, but certain elements want electrons more than others do. And so Linus Pauling discovered that fluorine is actually, he called it the most electronegative element, because fluorine just always seems to take electrons. And I think we already kind of knew that, because how many valence electrons does fluorine have? 7. How many does it really want to have? 8. If you like the analogy of like a King of the Ring cage match, fluorine's kind of like the big bully. Fluorine's the one that steals everybody's lunch money. Only in this analogy, the lunch money is electrons. Fluorine's got 7, it wants 8, and it's going to try to take one more. Does that make sense? Whereas there's other elements that are kind of the pushovers, and they're not really good at hanging onto their lunch money at all. For example, sodium. Sodium's a real pushover. I mean, sure, sodium would love to have a couple of electrons. It actually has 11, but it only has that one valence electron, and sodium just gives up its electron all the time. It's kind of like the kid who has to give the bully his lunch money, right? Every day he comes to school with an extra $1 to give the bully because he knows he's going to have his money stolen. Does that make sense? And basically, Pauling came up with a ranking system, which is kind of brilliant, actually, trying to figure out who would win in a fight for electrons between different elements. And we actually still use this scale in our periodic tables. So if you guys have your periodic tables nearby, for some reason I don't even have one here. So you can find your periodic tables. There is a number on your periodic tables directly above the letters, like say, for example, hydrogen. See how hydrogen over here in the corner, there's a number directly above it, 2.2. You guys see that value? And lithium, the number directly above lithium is 1.0. This is Linus Pauling's electronegativity scale, where basically he found a way to categorically rank the best fighter to the worst fighter in terms of how much they want electrons. Who has got the biggest number on this table? Way over in the corner, fluorine has been defined as having the best electronegativity, meaning that it wants electrons a lot. It's for some reason, even though it already has lots of electrons, it seems to want more. It's kind of like the hoarder of electrons, I guess. 4.0 is the biggest the scale gets to. Whereas as you go across the table and down the table, like say francium, francium's down at the very bottom corner down here. You can see francium, it's 0.7. Francium doesn't want electrons whatsoever. It's that pushover kid. A few other things I want to talk about electronegativity then. There is a whole column that has no number. There's actually a dash in that location. Can you guys see those ones? The noble gases. Helium, neon, argon, krypton, xenon, technically, we'll talk about that in a second. Radon. See how there's a dash in that location there? Why? They have no desire for electrons whatsoever. So even though francium is at 0.7 and really wants to get rid of his, things that are stable, they have no need for electrons. They don't want to get rid of them. They don't want to add more. They're basically stable. One of the weird things is that we've actually discovered, for whatever reason, again, chemistry is cool. I think it's fascinating. We've discovered some compounds that xenon can actually combine with. I don't know why or how. They don't even obey the octet rules. But xenon can actually combine with things we've discovered. So now it actually has an electronegativity of 2.6. Weird exception. I don't know, maybe one day we'll figure out why. Does that make sense? So what this allows us to do then is figure out basically who is more likely to take the electrons. Okay. There's actually 3 criteria that Pauling had to try to figure out this table. Honestly, it's well beyond even my understanding of how this works. So I know what he did. I don't even fully know the details why, but here's the 3 main things. Electronegativity is based on the distance from the nucleus to the valence electrons. Okay. Think of it like gravity. The further away you get from your planet, the less gravity is. Does that make sense? That means that the bigger the atom you have, like for example, if you want to compare lithium to francium, which one is bigger? Francium by far. Well, that means that your valence electrons in francium are so much further away if you're going to steal them. Does that make sense? Because in a way, it's like a planet where gravity is way less strong on francium because you're so far away from the planet than you are in lithium. And so if you were a bully trying to steal an electron, it's way easier to steal francium's electron than it is to steal lithium's. That makes sense? So, I mean, either way, lithium and francium are easy to steal electrons from, but one is easier just based on distance. Another thing that he discovered is that when there's inner electrons, those electrons that aren't part of the valence electrons, they sometimes can shield the nucleus. Because you know what ends up happening is like the nucleus is positively charged, electrons are negatively charged. Well, positives and negatives should attract. But here's the problem. Here's your positives. Here's your negative way out here. You got a bunch of electrons in the middle. Well, those electrons in the middle are kind of like a shield that prevents this electron from being held onto by the nucleus. So again, the bigger the atom, the less likely it is to be able to keep its electrons. So the long and short of it is, as you go down the table, electronegativity is usually dropped. The other thing is the number of protons in the nucleus. If you have more protons, though, the more likely you are to have a higher electronegativity. So usually as you go across the table, numbers get bigger. And it ends up working out something like this, where fluorine over here in the corner is usually the biggest. And as you go down this way, it usually gets smaller. And as you go back this way, it usually gets smaller as well. So usually these guys are very, very much like, these guys like electrons. And these guys over here, they really don't like their electrons. And this is the basis of what you guys probably already knew. This is how ionic bonds are formed. Where you have an electron, you want an electron, perfect. That's how I make a bond. The crazy thing, though, I already said this, is that the bond itself really doesn't exist. The bond is just mutually changing an electron. It would be like if Walker had $7 and I had $1 and I just gave Walker $1. Are we attached by anything? I mean, I gave him $1, I guess. But, I mean, in the chemistry world, that's what makes us have a bond. That makes sense? But really, there's nothing physically tying us in between us. Right? And it's the same thing in chemistry. There's actually nothing there other than just you change an electron with him. Here's some pictures just talking about then what we've already known. I hope you already know this stuff. The idea of you could have the transfer of electrons. That's an ionic bond. The one thing I haven't mentioned yet today, but you guys should know this already, there is also the covalent bond. Covalent bonds share their electrons. Have I given you guys the analogy before of like an ionic bond would be if something costs $8 and Walker has 9 and I have 7. And so he gives me one of his extra dollars and it works out that we both get 8. And that's an ionic bond where you have 1 extra, I have 1 too few, so we change and we're good. A covalent bond would be where I have 4 and Walker has 4, so we pool our resources till we get to 8. That's a covalent bond. Have we talked about that before? Okay. In order for this to happen, then the electronegativity is actually what helps determine whether something shares electrons or transfers electrons. In an ionic bond, if someone is really high on the electronegativity scale and someone is really low, there's a bully and a weakling that causes an ionic bond where someone takes, someone gives. But it's actually possible for two things to have a relatively similar electronegativity, and then they would share their electrons. If anything happens to make a bond, in usually the non-metal section there, everybody right about here has roughly the same electronegativity, and so no one really wins the fight for the electrons. If you like my analogy here, I'll use me and Walker since I'm using Walker today. Imagine that Walker is the big bully in the classroom and I'm the little weakling. Walker's going to steal my lunch money. That's an ionic bond. But imagine in this King of the Ring UFC fighter scenario here that it's not like the super heavyweight champ against the weakling here. But imagine that Walker and I are roughly at the same ability level. And we go into our fight for our dollar, and really at the end of the day, nobody wins. Does that make sense? Like maybe Walker wins by just like a little bit. Like maybe it's not a knockout, he wins on points. Well, in that analogy, that's a covalent bond, where really at the end of the day, we're just going to share. Does that make sense? So if it's a complete knockout of differences between electronegativities, it's ionic. There's actually a threshold, and I don't know that I have it written in these notes or not. So let's just write it here. If the difference in electronegativity is greater than 1.7, it's ionic. But if the difference in electronegativity is actually less than 1.7, we usually call it covalent. Let me do some examples once you guys write that down. Probably the most common example of an ionic bond that people start with is sodium chloride. What's the electronegativity for sodium? What's the electronegativity for chlorine? Okay, this is This is the only math you have to do in this unit. Can you subtract 3.2 and 0.9 from each other? I don't even need you to find the number. When you subtract these numbers, is it going to be bigger than 1.7 or less than 1.7?
Bigger.
Yeah, bigger than 1.7, right? It's going to be what, 2.3? So therefore, it's going to be ionic. Basically, what's happened here is in this electron fight, sodium doesn't fully give its electron away. They kind of tell you partial truths. Sodium keeps its electron kind of close, but it gives most of its electron away. And basically, chlorine wins this fight. And so that's why we call it an ionic bond. But let me do a different example here. A good example of a covalent bond would be like, say, carbon dioxide, CO2. It bonds covalently. Hence the whole carbon dioxide, because it uses the di as part of its word. What's carbon's electronegativity? 2.6? And oxygen, I believe, is 3 something. 3.2? 3.4. How far apart are those? 0.8? Is there a winner in this competition for electrons? Yeah, I guess technically oxygen wins. Is it a knockout? Not really. So they more share their electrons. I mean, technically ionic bonds, here's the secret we've been lying from you. Ionic bonds also share their electrons. They just don't share them very well. It would be, sometimes I have an analogy of when I'm sleeping in bed with Melissa, she will steal the covers for me, and I have like just a little bit left over. Are we sharing the covers? Yeah, but like I have just a little bit of sheets left over. Does that make sense? That's more like an ionic bond. She's more or less stole the covers. Whereas in this example right here, a 3.4 and a 2.6, technically someone has more than the other one does in terms of wanting electrons, but it's sharing. So we would call this a covalent bond. Does that make sense? This actually kind of fundamentally changes what we've taught you. Ionic bonds and covalent bonds are actually, technically they're based on how much they share electrons or they don't share electrons. If they share completely, then it's covalent, and if they don't share, then it's ionic. I think I can skip ahead here. We're getting to the end of class here. Here's an example of a covalent bond. Hydrogen and oxygen. Hydrogen is a 2.2. Oxygen is a 3.4. 2.2 and 3.4, it's kind of borderline, but technically it still actually is less than the 1.7 difference. So that's why we consider this to be a covalent bond. Okay. If they're far apart, it's ionic. Oh, we have a term for that. Ionic bonds, you should write this down or highlight this somewhere. The term we use for ionic bonds is they get held together with what's called an electrostatic force. Basically what ends up happening is, you know how like sodium right here, it has the extra electron, chlorine needs the extra electron. Chlorine kind of steals the electron. Sodium kind of maintains a little bit of possession of it, but more or less it's lost its electron. What ends up happening now is this guy has a positive charge, this guy has a negative charge. What do positives and negatives do? They attract. And the attraction, the name we have for it then, is electrostatic. So ionic bonds are held together electrostatically. Here's one of the weird things though. It's actually not a very strong bond. How do you break an ionic bond? Well, one of the very first things we learned about in Chemistry 20 is the term dissociation, dissolving things. Do you guys remember that term from way back when? If I were to give you NaCl solid, an easy way to break this bond is to make it Na plus and Cl minus. All you gotta do is add water. Remember that analogy of all those little first graders who overrun you and tear you apart? Ionic bonds are actually fairly weak. Even though you've got positives and negatives attracting each other, water can easily rip them apart. So it's actually very easy to break a bond when it dissociates. The last thing I want to talk about here, I think I'm almost done here, is a type of bonding that we haven't covered yet. I don't imagine you've heard this before. It's called metallic bonding. And basically metals undergo metallic bonding, and they bond with themselves. So this would be like, imagine you have a sheet of copper. So this guy right here is copper, this guy's copper, this guy's copper, this guy's copper, this guy's copper. Okay. And what ends up happening is all of these coppers, they stick to each other and make like a firm, solid piece of metal. And the reason why is the metallic bonding occurs where the electrons, the term we use is they become delocalized. Which, I mean, if you kind of put all those terms together, did I use delocalized in here? Here it is, down there. What would local mean to you? Sure, close to home. Right? All of these electrons normally have a home. Right? Copper either has 1 or 2 valence electrons, depending on which charge we're using. Right? Which means that it has electrons kicking around. Well, normally these electrons, I would say there's 1 attached to each one, but they become delocalized, and these electrons can kind of go wherever they want. Hence the delocalized. And it actually forms a bit of a glue between these substances. I like to think of a Rice Krispie square myself. You know how like a Rice Krispie square has all the little Rice Krispies in between there? And then there's that like marshmallowy goodness in between there that keeps it all stuck together? That's kind of what happens in metals. Something that is a metal, like this, the reason why it's structurally held together is actually again because of the electrons. And this carbon and this carbon and this carbon and this carbon, the electrons they all have, they just kind of swarm anywhere. It actually leads to a really important properties of metals. If electrons are allowed to move, they conduct electricity. That makes sense? And that's actually one of the that fits together here. The idea that in metallic bonding, it's all just the same thing, like magnesium, magnesium. Actually, maybe that's a poor choice. Let's do iron. All these iron stick together because these electrons, they basically go wherever they want. And because of that, it conducts.
Please excuse the interruption. Here are your announcements for today. The gym schedule for tonight. B girls, you're practicing at 3:45. B boys at 5:15. A girls, 5 o'clock in Granham. A boys, 7:15 tonight. The lunch special today is a bacon cheddar burger with a creamy coleslaw. The following students need to see Mr. Orr at the lunch bell in the shop. Jack Austin, Lexi Cheesecap, Brandon Creighton, Reyes Eagletail Feathers, Hayes Gillingham, Tom Hawarda, Jesse Light, Louis Nito, Sydney Perry, Bradley Van Herk, and John Zamirchuk. Please go see Mr. Orr in the shop at the bell. Just a reminder to the senior high students, it's Flex Friday, this Friday, January the 8th. High school breakfast cart volunteers are needed. If you are interested in helping with the breakfast cart, please see Marty for more information. Work experience hours are available for this position. Staff supervision, Team 3 is on supervision today. Also a reminder that the grad bottle drive is on Wednesday. Please pick up your forms from Noni in the library. Can the following students please come to the office at the bell? Dominic Scully, Ellie and Tate Healy, Maddie Orr, and Joper Paggio. Please come to the office.
Okay, quick summary here, then we can take off. This is one of those lessons where if it feels like you didn't learn anything, that's probably okay, because a lot of this was maybe quasi-review, some new stuff. This is one of those lessons though where I feel like I have to tell you I've been lying to you for the last little while. Ionic and covalent bonds are actually not what I used to think they were. When we actually teach you guys in grade 9 and grade 10 about ionic and covalent, we teach you a bit of an older definition because it's a little bit easier to work with. The better definition now is based on electronegativity. There's like a king of the ring concept where certain things, they want electrons more than others. If between two atoms, the electronegativity is very far apart, it usually makes what's called an ionic bond. Ionic bonds are actually very weak, actually. It's actually not a good thing. If the electronegativities are relatively close to each other, and they're both high electronegativities, it means they both want their electrons. It means that they share their electrons. That's a covalent bond. The last possibility is that you have two very low electronegativities, meaning that the electrons are delocalized. Nobody wants electrons. This carbon, or this copper, this copper, this copper, this copper, none of those copper want their electrons. So the electrons just kind of go wherever they want. The cool news about that is that's actually very strong. If you want to compare, say, salt, which you can destroy by putting it in water, or a piece of copper metal, And granted, copper will actually rust in water, but ignoring that fact, it's actually sometimes much stronger if nobody wins the fight for electrons. Does that make sense? So in terms of strength, metals are actually very strong because nobody wants the electrons. So the electrons just kind of go wherever they want, and it makes a firm sheet of metal. Okay. The last thing here, these terms I need you guys to know. Valence orbitals, the idea that there's that three-dimensional region of space, and make sure you get the idea of this electronegativity, the concept of how there's a competition for who can take the electrons. Some people want them, some people don't. And that's what helps keep our matter together. Because if there's a strong bond, it's a solid. If there's not strong bonds between things, that's what makes them liquids and gases. Does that make sense? Alright, cool. Well, you guys can take off. I'll see you in math, I guess. By the way, there's one more thing else we're going to do in math today. If you guys can print those off some way. It's real short. It's going to be half an hour. Oh, thank you. Let's make a folder here. Or make a pile, I guess. Oh, I need to rest my voice.